some people to cancer, or enable new therapies for HIV, or edit the genes that cause hereditary diseases. In the plant world, it could make crops more nutritious, disease-resistant, and able to grow in difficult conditions. By editing animals' genes,
together, they form a complex that can identify and cut specific sections of DNA. First, Cas9 has to locate and bind to a common sequence of the genome called a PAM. Once the PAM is bound, the guide RNA unwinds part of the double helix. The RNA strand is designed to match and bind a particular sequence in the DNA. Once it's found the correct sequence, Cas9 can cut the DNA. Its two nuclease domains each make a nick, leading to a double-strand break. Although the cell will try to repair this break, the fixing process is error-prone and often inadvertently introduces mutations that disable the gene. But making double-strand breaks isn't all CRISPR can do. Some researchers have deactivated one or both of Cas9's cutting domains using new enzymes onto the protein. Cas9 can then be used to transform those enzymes into a specific DNA sequence. In one example, Cas9 is fused to an enzyme, a deaminase, which mutates specific DNA bases, eventually replacing cytidine with thymidine. This kind of precise gene editing means you can turn a disease-causing mutation into a healthy version of the gene, or introduce a stop code at a specific place. But it's not all about gene editing. Several labs have been working on ways to use CRISPR to promote gene transcription, activating Cas9 completely so it can no longer cut DNA. Instead, transcriptional activators are added to the Cas9 by either fusing them directly or via a string of peptides. Alternatively, the activators can be recruited to the guide RNA instead. These activators recruit the cell's transcription machinery, bringing RNA polymerase and other factors to the target and increasing transcription of that gene. The same principle applies to gene silencing. A crowd domain fused to the Cas9 inactivates the transcription by recruiting more factors that physically block the gene. A more outside-the-box idea for using CRISPR is to attach fluorescent proteins to the complex, so you can see where particular DNA sequences are found in the cell. This can be useful for things like visualizing the 3D.
Hello, I'm Nomruddin Mukherjee and I'm from Vidyasagar University. I have attended this seminar and this workshop helped me a lot. I did not have a clear concept about docking, but this workshop gave me a clear concept about docking. That's it. You can join here for your better future.
Hi all, I am Jatendra Sachdeva from Shulini University. I am pursuing BTech Biotechnology SRP there. So here I came to Delhi to attend this workshop on the drug discovery and genome editing. I think it was really helpful for me and I would like to recommend to my friends also the same, and I got to know new things and hands-on training on the different softwares which I really wanted to work with, on which I googled but I could not use them or apply them in daily life situations, and here I could work on them and I got the idea how to use them. So it was really nice, and then the basics were also taught, so I really liked this session. Thank you.